This week I'm going to present some equations that predict the temperature of a heatsink based on the amount of heat that is given to this heatsink. This figure shows the experimental data. Particularly, this graph is the experimental data, which I'm going to open in a new tab. This is the experimental data for the 7.6 centimeter wide heatsink that I will show later for different lengths from 20 centimeters all the way to 60 centimeters at an interval of 10 centimeters. To have some equations for these graphs, I used a fitting algorithm in Python, and of the form a times x to the power of b plus c. I'll explain why later I chose this kind of equation. So these other three graphs show the value of the coefficients of that equation, and I will explain a little more about them, particularly this one later. This is the heatsink that I used for the measurements. The length increases in this direction and in this other direction. The heater is always located at the middle of the heatsink, and the heater is a polyimide heater from Omega model. This kind of model, KHVLA 303-10. The direction of the heatsink is with fins pointing upward, and the type of dissipation is passive dissipation. There is no fan. Considering all this considering this setup is the way in which I got the temperatures that I showed in the previous graph. While I have been doing the measurements, I have always observed that for the case of passive dissipation, a linear fit is not always very accurate, as it seems that the behavior of the temperature of the heatsink varies with the amount of heat given, and it is not a linear relationship, or at least it doesn't adjust to a linear behavior. So, and that is a way most thermal resistances are, a lot of thermal resistances for heatsinks are given as a value. That is the coefficient of a linear equation. That thermal resistance value is the coefficient A in this equation. And in my experience and in all the measurements I have made, this doesn't seem to be a good fit. So I decided to create a better fit, despite not having right now a good physical explanation as to why this fit is better or has a more rigorous backing than a linear fit. But what interests me more now is that I have an equation that actually predicts with better accuracy the temperatures and that I have gotten. So that's why I use this fit. This is the equations for each length: 20 centimeters, 30, 40, 50, and 60. The behavior that is most clear from these equations is that the coefficient A has a monotonic decrease in value as the length increases, which means that the thermal resistance decreases. And therefore, the temperature will be lower for the same amount of heat given to the heatsink. I will put a link to this page in the description in this video, so you can have these equations as a reference. Well, that's it for this week, and thank you.